Thank you. Hi, everyone. I'm Frederick. I'm a master's student at the Department of Geological Science and Geological Engineering at Queen's University in Kingston, Ontario. And I'll be presenting preliminary results of my research on the influence of submarine channel sinuosity on grain size sorting of channel and levee deposits. I'm being supervised by Dr. Elizabeth Steele, and I'd like to acknowledge some of my colleagues who have been helpful during this research, Hila Uzaid and Arjun Chatupadia. Just a bit of background. In the past research, I've actually looked at the interaction of topsy current with submarine channel. However, this research have actually focused on the relationship between submarine channel and topsy current flow properties such as sediment grain size, suspension cloud concentration, flow velocity, and the likes. But the effect of channel element such as sinuosity on topsy current and on resulting deposit is fully not well understood, and that's what this research looks to throw more light on. Currently, what we know about interaction of topsy current with sinus submarine channel is that there's occurrence of sorry, I'm just gonna take my pointer here. No, not that. That's not what I want. Yes, so currently what we know about topsy current interaction with sinus submarine channel is that there's occurrence of deposition at channel bend, and this has been pointed out by Janako et al. In their 2013 paper where they used laboratory experiments to show that as topsy current tries to negotiate through channel bend, there's often deposition within the channel as channel field deposits and also at adjacent inner and outer levee areas. They also use numerical modeling to show that there's mixing of suspended sediment at channel bend. Again, they show that as the current tries to negotiate through the bend, the current collides with the channel walls, and this flow collision results in some secondary circulation cell that is capable of transporting sediment to the outer bank area and even bypassing the channel bend. So given what we know about the topsy current interaction with sinus submarine channel, we are looking to test two hypotheses with our research. We're looking to see if increasing channel sinuosity will lead to finer sediment bypass through channel bends, and if increasing channel sinuosity will lead to better sorted channel field deposit as well as inner and outer levee deposits. So we employed, to test our hypothesis, we employed laboratory experiments. This is due to the difficulty and complexity in monitoring real-time topsy current as well as their rare occurrence. So we are using laboratory experiments. Our experiment was conducted at the flume facility at the Coastal Engineering Laboratory at Queen's University. The flume is 4 meter by 4 meter and 1 meter deep. I'm standing right beside the flume, so you can use me for a sense of scale. I am about 1.3 meters tall. We built 4 channels with varying sinuosity from 1.0 for straight channel to 1.35 for our most sinus channel, and we released topsy current into each of these channels. Our topsy current consisted of 2 distinct sediment types. We used the grounded walnut-shell and melamine. Melamine is a plastic sediment. And then after each experimental run, we take samples where we use that to do a laser diffraction grain size analysis using a mastersizer. And before and after each experimental run, we profile the channel that we have built just to see the change in terms of deposition and also be able to do some calculations as regards sediment deposition. So for experimental setup, so we built 4 channels, like I said. They are non-erodible channels. If you look at the top right, you see what our channel looks like. Channel was built out of a mixture of silica sand and clay, particularly bentonite. And we sent topsy current through this channel. Topsy current consisted of 2 distinct, topsy current consisted of sediment concentration of 3% and 1.5%. So for each of our channels, for each of our channel, we sent topsy current of 3% and 1.5% through them. To properly isolate the effect of channel sinuosity and understand how it affects sorting and grain distribution, we kept the basin slope constant. So the basin slope is the platform here where the channel is lying on. It was held constant at 3% at 3 degrees, and we also had the topsy current discharge rate at 2.7 liters per second throughout the experiment. Every other parameter, including the channel dimensions, were all held constant. This is to properly help us isolate the effect of channel sinuosity. The image at the bottom just shows what our channel looks like when it's underwater and when it's ready to go. I put this video here just to give you a sense of what our experimental run looks like. This is run 2 with sediment concentration of 3% and channel sinuosity of 1.25. I'm just going to go ahead and play it. Actually, oh, sorry. Okay, I think I'll just go ahead. So I was just going to show you guys, if we release, when we release the current into the channel, the current often overtops the channel walls. which is a common characteristic of turbidity current. And then as the current tries to negotiate through the bend, there's often spillage. So the current overspills sediments to the outer levee areas as it tries to negotiate this bend. And then there's a reduction in the flow velocity. Also, as the current encounters at channel bend 2, the current also spills out its contents to the outer levee areas predominantly, and a significant reduction in the flow velocity. This is what we have noticed for all our channels, but then we noticed that this process of spillage and reduction in flow velocity becomes pronounced as our channel sinuosity increases. So for our grain size analysis, we use walnut-shell as a proxy for fine sediment, and the melamine, which is plastic sediment, as a proxy for coarse sediment. But if you look to the right, you see the plot shows that the grounded walnut-shell is actually coarser than the melamine. However, the melamine is more dense than the walnut-shell, so it has higher settling velocity. So in the mixture, it settles faster than the grounded walnut-shell. That's why we have used it. That's why we have used the plastic melamine as a proxy for coarse sediment, because it's denser than the walnut-shell. So, like I mentioned, we took underwater laser scan before and after each experiment, and the idea is to help us when we process this laser scan, we can actually identify areas of significant sediment deposition, and this will also allow us to determine the volume of sediments that were deposited in different areas. So here is a raw laser scan data that we collect, and then when we process it, this is what it looks like. The red shows areas of significant sediment deposition. Currently, we are still processing underwater laser scan data, so we do not have results for them right here. But what we have is our result from our grain size analysis, where we can actually see some interesting trends in terms of sorting and grain size distribution. So after every experimental run, we let our samples, we let the sediment settle and get deposited. We empty the basin, and then we collect samples for grain size analysis. We collect samples from the channel bends, the channel bend 1 and channel bend 2, and also we collect samples from the most distal part of the channel, which I have termed channel end. So at channel bend 1, we take sample of the channel fill, we take sample of the inner and outer levee deposits. The same thing is done here. The red indicates the channel fill samples, where samples are taken from the channel fill, and then the blue indicates areas where samples were taken from the levee areas. And over here at the distal end, we also take samples from the channel end fill. So for our result, what we have here is grain size analysis for turbidity current with sediment concentration of 3%. We are still processing all of that result, but interestingly, we are already identifying some trends in terms of grain size distribution and sorting as sinuosity increases. So on the left, you see our channels from run 1 all down to run 3, that as sinuosity increases, well, the only channel that is not here is the straight channel, which we do not really see any trend. But then our grain size analysis just shows us the percentage of coarse and fine sediments being deposited in different areas, and the red dot shows areas where samples were taken from. So for run 1, at channel bend 1, which is right here, which is the first channel bend, we see that there's more fine sediment being deposited here than coarse sediment. But then as we go down to the more distal channel bend, that's channel bend 2, we see that there's about equal amount of coarse and fine sediment deposited here. While down to the channel end, that's the most distal part of the channel, we see that there's more fine grain sediments being deposited here than coarse grain sediments. So we did this for all our channels, and then we could interestingly see very evident trend in terms of grain size distribution and sorting. And then if you see that the samples that we collected from the channel end for all our channels shows that as sinuosity increases, so sinuosity is increasing downward, we see that there's progressively higher amount of fine grain sediments being deposited. So we can see that at the channel end deposit increasingly become dominated by fine grain sediments with increasing sinuosity. So as we increase the sinuosity of the channel, we have more fine grain sediment making it to the channel end than coarse grain sediments. And the deposits are better sorted with increasing sinuosity. So if you look at this over here, you see that as you go down, as the sinuosity increases, the deposit gets increasingly better sorted. And in the same vein, we looked at the levee areas to see how the increase in sinuosity actually affect deposits of inner and outer levee areas. So this is for channel bend 1. So these are deposits taken from the levee areas of channel bend 1. And then we see that at channel bend 1, for run 1, we are seeing that there's more coarse sediments being deposited than fine-grained sediment. But then at the outer levee, we see that coarse sediments begin to dominate, and then we have very little of fine sediments being deposited. But as sinuosity increases, we see that the trend actually changes, where there's an increase in fine-grained sediments being deposited as we increase sinuosity again, which then corresponds to what we are seeing from the channel field deposit. So with that, we can say outer levee deposits become fine sediment dominated with increasing sinuosity.
2 minutes left.
Okay. We did the same thing for the more distal levees, more distal levees, that's levee at channel bend 2, and then we see that again we have high amount of coarse sediments being deposited, but then as we go down the channel, as we increase sinuosity, we again see that the outer levee deposit gets dominated by fine-grained sediments. So this corresponds with what you saw at the channel bend 1. The outer levee deposit become fine-grained and dominated with increasing sinuosity. And interestingly, at the more distal levees, we are seeing that the inner levee also is being dominated by fine-grained sediments, which shows that fine-grained sediment dominates distal levees with increasing sinuosity. So this can we can interpret this as being that we have more fine-grained sediments bypassing the channel bend at channel bend 1 and getting deposited at the levees at channel bend 2. And also distal levees are increasingly better. So if you look at as the sinuosity increases downward, you see that deposits get better sorted with increasing sinuosity. So this brings us to our conclusion with our preliminary results, because we still have other results that we are processing. But with what we have seen from the trend, we can see that channel field and outer levee deposits become increasingly fine-grained, and they get better sorted. So if you look at the channel end deposit, you see that as the sinuosity increases downward, you see that they get dominated by fine-grained sediments, and they are better sorted for the channel end deposit, outer levee deposit at channel bend 1, and even the more distal outer levee deposits. And then we can come to a conclusion to say that the increasing sinuosity leads to reduction in coarse sediment bypass at channel bend, because the reduction in the flow velocity actually results in coarse sediments being deposited at channel bend. But then we can't say with confidence that it actually favors fine-grained sediment bypass until we finish our laser scan interpretation to actually see the volume of fine-grained sediments that have been deposited at the channel end area. Yeah, I think that's it. Thank you for listening.
Thank you very much for this wonderful experimental data, Frederick. We have one question already coming in from the audience, a question by Edson Martinez. How long does it take to simulate this model of channel filling?
So basically, our experimental run for each lasts about 30 seconds. So we just we build the channel, which is quite time consuming. We build the channel, we fill up the basin, and then we send up the current. So the top of the current runs for about 30 seconds, more or less.
Yeah. Okay, and a second question from the audience asked by Kevin Rees. How do you know that the channel sinuosity was responsible for the observed decrease in coarse grains at the channel end, instead of the grain size fallout with distance?
So basically, we looked at, can you hear me?
Yes.
Okay, so basically we looked at the deposit at the levee areas to see how the deposits at the levee areas correlate with the deposit of the channel field, to know if we have more coarse sediments being spilled over. But then it shows that we even have more fine sediments being spilled over at the levee areas. So we couldn't have been losing coarse sediments at the levees, rather we are losing them right in the channels. They are being deposited as the flow velocity reduces as the current tries to negotiate through the bend.
Yeah. So we include the deposit thickness in a way in that analysis as well.
Yes, exactly. So we intend to do that when we get our laser scan, because that will actually help us determine the volume of coarse and fine-grained sediments deposited in different areas.
Yeah, that's a very good idea. I also have one small question about the flows. You mentioned the flow velocity trends, but what were approximately the flow velocities of these experimental currents in the channel?
So basically, we didn't determine the flow velocity, but we could only see from because we have high-end video cameras that could show us that as the current tries to negotiate through the bend, there's a significant reduction in the flow velocity, but we didn't actually determine the flow velocity.
Okay.
But we could tell from the video cameras that there's a significant reduction in the flow velocity, which I think you would have seen clearly if the video had played.
Yeah, I understand. And if you would, so you could perhaps see the frontal propagation velocity from the video camera. So how fast does the front propagate? Is it 10 centimeters per second, or 50 centimeters per second, or a few centimeters per second?
So yes, that's a good question. It's something we didn't really look into, but I can tell you from average is about less than 10 centimeters per second.
Okay, yeah, thank you very much. That satisfies my question very well.